let's talk about quantum numbers. So, in the last video, I just briefly explained where the quantum numbers come from. So just to remind you, the quantum numbers come out of the Schrodinger equation. So when you solve the Schrodinger equation for the wave function of the electron, you find these integer values in all these different wave functions. And those integer values control the size and shape of the orbital that the electron is sitting in. To help us understand really what these quantum numbers are useful for us, what they're going to help us do, I like to think of an analogy of a warehouse. If you've ever worked in a warehouse before, you have this giant room, and there'll be rows of pallets or cabinets or something that you're storing material in, and usually these rows of materials are numbered. You have to have some kind of an organization that will allow people to come in and say, okay, I'm looking for this thing, and you'll be able to look it up in the system and say, okay, well that thing is on row 2, and it's on the third pallet down, and it's in this particular box on that pallet, on that row. So there is an organizational system for any kind of warehouse system like this, or at least I sure hope there is. Otherwise, you're just going to have a hard time finding stuff. So if you have a good filing system for a warehouse, it is very easy to figure out where something goes, either if you need to go and find it or if you need to put it in the correct place. If you have a good filing system, you know where everything goes. The quantum numbers are just a filing system for electrons in an atom. They tell you where an electron goes and all the possible different places that an electron could go in an atom. To kind of carry the analogy further, if in a warehouse like this, you'll have big rows, and then you can have the rows split up into individual sections, and then you can have individual boxes on those individual sections. We can split the quantum numbers up kind of the same way, because each of these quantum numbers kind of builds on the last one. So the first quantum number is what we call the principal quantum number. It is usually represented with the letter N, and the principal quantum number tells us the shell that the electron is in. And the shell is like a row of pallets in a warehouse. It's the biggest group of things. There's a lot of stuff inside of a shell. The next quantum number is usually written as a cursive L. That's what that's supposed to be. And this is the angular momentum quantum number. It is sometimes called the, I think I know how to spell it, actually no, that's not right. Azimuthal. It's kind of the old-fashioned name for this, is the azimuthal quantum number. It's more often referred to now just as the angular momentum quantum number. This tells you the subshell that the electron is in. So we have the shell, the broadest, least specific number, and then inside that shell we have one or more subshells, just depending on the shell, which we'll talk about in just a second. So we have the shell, the subshell, which is determined by the angular momentum quantum number. So that would be like saying, if the shell is the row of pallets, the angular momentum quantum number is like saying this specific pallet in the row. The next quantum number is the magnetic quantum number. And this is like the box on that palette. It's saying, okay, in this subshell, we are looking in this specific orbital. So we have the shell, the row that the electron, so to speak, is on. The angular momentum quantum number, which is the palette on that row. And then inside that palette, or on top of that palette, we have the magnetic quantum number, which tells us the specific box that the electron, or the thing that we're looking for, is in. And then the last quantum number here is what's called the spin quantum number. It's the least complicated of the three, because it could only ever be positive 1/2 or negative 1/2. So if you want to go ahead and continue the analogy with that, you can think about it in terms of, in our very strange warehouse, we could only ever fit 2 things in a box. And so this just tells you which of the 2 things. Either the one that's pointing up in the box or the one that's pointing down in the box, which one you want. So this is, I think, the best analogy I have for what the quantum numbers actually tell us. It's a filing system for electrons in an atom, and these 4 numbers tell us exactly where in the atom the electron is sitting, exactly where it is. So these 4 quantum numbers tell us where an electron is. Every single electron has 4 values, has a value for each one of these 4 things. And no 2 electrons can have the same 4 quantum numbers. This is what we call the Pauli Exclusion Principle. So if you have one electron where its 3 values for the its 4 values for the 4 quantum numbers are 1, 1, 0, and 1/2, you cannot have another electron that has those same 4 values. You could have an electron that is 1, 1, 0, and minus 1/2. That's perfectly fine. Or you could have 2, 1, 0, positive 1/2. As long as one of the numbers is different, that's fine. That's perfectly fine. You just can't have 2 electrons where all 4 of them are the same thing. Alright, I think in the next video I will get into how these different orbitals are separated, so to speak, how they sit inside of the atom, how they're grouped together inside shells and subshells, and how many orbitals specifically there are in each of these subshells and shells. And so we're going to get into that in the next video when we start talking about the values for these quantum numbers that are allowed. Because we can't just pick willy-nilly what these numbers are going to be. There are very specific values that they are allowed to be. And if we understand those rules, it'll really help us in writing electron configurations. So I'll see you in the next video.